Hi, my name is Matthias Heinrich. I'm a lecturer at the University of Lübeck, and for this MICA Educational Challenge, I'd like to introduce you to the concept of discrete optimization for medical image registration. Let me start by first motivating why we're doing medical image registration. It is useful for a number of important clinical tasks, including the fusion of images acquired from different modalities for image-guided surgery, to compensate motion for adaptive radiotherapy, for example using the CyberKnife. And for this, we need to estimate respiratory motion for a patient using 4D-CT. We can also use it to automatically segment images using expert annotations of training data and atlas-based segmentation. For all these tasks of image registration, we're required to find correspondences across scans. And these correspondences should match related anatomical locations in the fixed and moving image. And we can then define a dense correspondence field by an identity transform and a displacement field U of x. This can be done automatically by optimizing cost function. And this usually consists of at least two terms, a similarity term and a regularization term. Let's have a look at this exemplary cost function plotted against the parameter value. We can find a minimum for this by using continuous optimization. We first initialize it, calculate the derivative, and follow along it downwards the gradient. After a number of iterations, we end up at a minimum, which in this case is only a local minimum. In contrast, discrete optimization allows us to optimize over a large range of quantized transformation parameters simultaneously. The advantage is that it avoids the local minima, and we find an optimum very close to the global one. Discrete optimization can be optimized using graphical models, such as Markov random fields. A graphical model consists of a number of nodes. In our case, they correspond to either voxels or control points. I've called them VP, VQ, and VR, and I'm plotting a couple of them here. Next, we introduce edges, which connect nodes, and are drawn with green lines. They should model the interactions between nodes. And thirdly, we have a set of labels, Li, Lj, Lk, which correspond to 3D displacement vectors. They are hidden variables of our nodes. The aim is now to find an optimal labeling which assigns a displacement vector to each of the nodes. And the quality of this labeling is evaluated using again a cost function which consists of two terms, R of Fp and Fq, which is called the pairwise potential, and D of Fp, which we call the unary potential. The unary term usually models the similarity between images. And since it's independent for each voxel or control point, we have a very great control over the space of potential displacements. We can use a sampling simply along the axis, a planar sampling, or we can evaluate every possible 3D displacement within a cube of a certain search range. The animation on the left shows how we calculate similarity between the red block in the fixed image and a green block which is shifted densely over the moving image. Because we don't require a derivative, we can use or point or patchwise similarity measures, such as the sum of absolute differences, normalized cross-correlation, or the self-similarity context. And this yields us with the similarity distribution as shown on the left, for every control point. But up to now, we haven't included any regularization. And this means that the resulting displacement field, which I will show here in a certain specific color coding for 4D-CT registration, may contain many implausible irregularities. For example, folds in transformation or unrealistic local volume change. So we would like to use the pairwise potentials to include a penalty for deviations of connected nodes. And one potential choice would be the total variation, which is based on the absolute difference of displacements. and has a cost function which looks like this. Or we could imply diffusion regularization, which penalizes the squared difference of displacements. If our algorithm consists of multiple steps, it's always useful to perform an incremental regularization. So for general graphs, this optimization is unfortunately NP-hard, and its solution is only approximated by using algorithms such as graph cuts or message passing. However, for a certain relaxed graph structure, which contains no loops, namely a tree, we can find the exact solution using dynamic programming in linear time. And I've prepared a very simple example consisting of only 4 connected nodes, which each can take one of the following 5 displacements between minus and plus 2. We use total variation as regularization penalty, and the unary potentials are represented by the height of these 3D bars. We now aim to find the path with minimal cost across these obstacles. To make this more accessible, I've written down the numbers of the unary potentials in an array. And we'll work our way up from the green node up to the blue node. Let's first try this specific path, which takes always the 5th label. It only has unary potentials, which add up to 8.5. Secondly, look at this diagonal path from 5 to 4 to 3 to 2. It has a total unary cost of 4 plus a regularization penalty of 3. We can easily realize that by increasing the number of nodes, the potential solutions increase exponentially. So no useful problem could be solved using this brute force approach. We therefore explore a recursive solution on the next slide. To work out this recursive solution, we need to define 2 additional matrices. One which stores the cost of any optimal path up to a certain point, and another one which stores the indices of the labels which got us there. The equation for the recursive formula calculates a message vector by minimizing over the unary potentials d, the message vector m, and all the possible pairwise combinations of the regularization term r. For the green node, we have no previous dependencies, so we can simply copy the unary potentials here. Let's evaluate the message for the 3rd label of the yellow node. Here we have 5 potential paths which lead us here, and we have to calculate the cost of each of them. The first one has a cost of 0.5 plus regularization term of 2. The second one has a cost of 1 plus 1. A third one only has a unary cost of 3. And the remaining 2 ones both result into 3.5. Once we're finished, we simply select the minimum and write down the argmin, which is the label where the path originated from at the green node. So this is 2 in our case. And we write it into the respective box of the index matrix. The cost matrix should store the sum of the unaries and the messages. So we add up 1.5 to our message 2 and write down 3.5 into the yellow box. We can now repeat this process for the remaining labels of the yellow node and fill out the optimal costs and label indices. And we can perform this message calculation following the same principle for the red node and the blue node. And since the blue node doesn't have any further dependencies, we can simply select the minimum with a value of 6.5 and a label of 2. And to find the optimal path, we now simply need to trace backwards through our index matrix and select the second label of the red row, the third label of the yellow row, and again the third label of the green row. So this leads to a path 2, 3, 3, 2. And we can simply check that this actually adds up to a cost of 6.5. To speed up these message calculations, we can use distance transforms for commonly used regularization penalties as introduced by Felsenschwab. Next, I'd like to show you a real-time example of our approach using the software framework called Deeds. This is a live demonstration of the software package Deeds, short for dense displacement sampling, which I've developed during my DPhil at Oxford. I first start running the algorithm in a terminal window and explain the graphical user interface in the meantime. In the first two rows, we can specify the input and output images. Here I've selected the inhale and exhale phase of a 4D CT scan of the Dillop dataset. Next, we set the parameters for the control point spacing and the search space. The framework uses 5 scales in this example, so we have to set 5 values each. Finally, the similarity metric and its relative weighting are chosen. Here I've used the self-similarity context. Now the registration has finished in shortly over 30 seconds, and we can have a look at the visual outcome it generated using animated GIFs. The top row shows the overlay of the images before registration using green and magenta colors in an axial fly-through. And below we can see how the differences almost entirely disappear after applying our deformable registration. On the right hand side, the magnitude of the estimated deformations is shown in a false color coding for a coronal view. It can be seen that the sliding motion of the lungs is well preserved. Finally, I'd like to summarize the key advantages of discrete optimization. First, it doesn't require a derivative of the cost function, which makes it very flexible. Second, we can approximately find a global optimum. And third, if we use an efficient implementation, we can achieve a very fast registration. There are many active topics of research in this area. The use of advanced transformation models, for example curvature regularization and linear or symmetric transforms, exploiting uncertainty estimates for dynamic search range refinement or to improve segmentation propagation, the estimation of extra parameters in addition to the geometric displacements, for example a segmentation label or functional imaging parameters, and finally the use of image adaptive non-grid graphs such as supervoxels or finite element meshes. For further information about this mini lecture, you can have a look at the website mpheinrich.de/mec.html, where you can find source code, additional references, and a transcript.